looking at Ohm's Law and the definition of current. Actually, let's do a few little clicker questions. You can just go in the back. What is the correct way here to light the light bulb? General idea that with a circuit we have to have a complete circuit, that we need a complete loop for the current flow. I just want to remind you, I pointed this out early on in chapter 2, but when we talk about, I think I pointed this out, maybe it was in math, but when we talk about voltage and current, we talk about them in different ways. We talk about how we measure the voltage across 2 points, or between 2 points, and we measure the current through something. That when we're measuring potential, we're measuring the difference in energy between 2 points. That's why we say the voltage across, or the voltage, the voltage across something. And we measure the current as it travels through something. And y'all saw that in lab when you measure voltage and current. All right, let's stop at 1 minute. It's 7 more seconds. 1 minute. Where are you people today? Is everybody on here? All right, we'll stop right there. Okay, good. C is right. In order to have a circuit, you have to have a complete circuit. So electrons are protons, we plan on will flow in this direction through that circuit. And you don't have a complete circuit in the others. You double the voltage across a certain conductor and you observe the current increases 3 times. What do you conclude about Ohm's law? Is it obeyed, or is it not obeyed, or does this just have nothing to do with Ohm's law? All right, let's stop at 45. You'll remember the ladies softball. They're playing in a tournament. I guess if the weather is well this afternoon. Playing in a tournament this afternoon. And then they have a game next Tuesday at 5. All right, good. B is the right answer. Ohm's law is not obeyed because Ohm's law says that the voltage is proportional to the current by this relationship. So this says that if you double the voltage, then it's saying that you triple the current, but that's not the case. If it's an ohmic device, that is something that follows Ohm's law. If I double the voltage, I double the current. That your voltage and your current are related linearly. We'll look at ohmic versus non-ohmic devices soon. I'll talk about these graphs. Let's see, have we talked about this actually? Let me know that we have. No, so let's we'll come back to this. All right, so Ohm's law applies to most materials for which their resistance is constant over a wide range of voltage and current, meaning that the voltage is proportional to the current, or vice versa really, that if we provide energy in voltage, then that provides current. And if I increase my voltage by a certain amount, I increase my current by that same amount, by that same factor. Materials that do follow Ohm's law are called ohmic. But for non-ohmic materials, for an ohmic material, you would get a graph that looks something like this. And if you remember, you guys will do this in the lab if you haven't already, but V is equal to IR. And by the way, I think you have an OpenStax question that is similar to this, a tutor question, that V is equal to IR. So I then is equal to 1 over R times V. So from that, if I have a plot of I versus V like this, then the slope of that graph is equal to 1 over R. Right, I just take my Ohm's law and write it so that I is on the Y, in the Y position, and V is in the X. and then the coefficient of my x variable is the slope of that graph. And so if I plot the current versus the voltage, as you'll do in lab or you have already, you'll find that the slope of that line is 1 over r. Now for a non-ohmic device, you can have something that where you continue to increase the voltage and the current doesn't change. You add more and more energy to it, but it doesn't change. But at some point, you reach a threshold where it does change. This is a non-ohmic device. They can do various things. We're not going to get into solid-state devices in this class, but transistors, for example, and diodes are non-ohmic devices. They can be useful because they allow the flow of electricity in one direction, but not in the other direction. So you might have seen a diode in an electrical diagram, an electric circuit diagram. A diode is usually like this. You don't need to know this, I'm just sort of showing it to you. A diode usually looks like that. It's drawn like that because it allows current to flow in this direction, but not in the opposite direction. All right. Again, we're not going to use diodes or transistors in any way in this class, but just know that there are devices that are ohmic, like resistors, copper wires, ohmic, for example, and then there are these solid-state devices that are non-ohmic. Let's see. Let's try this one. This one's very similar to the one you just did. You apply 3 volts to an electrical device, you get 2 amps. When you apply 6 volts, the current is 3 amps. Is this an ohmic or non-ohmic device? Really asking, is this a linear relationship between V and I? If it is, it's ohmic. If it's not, it's non-ohmic. Okay, doing a good job. I'm going to stop here at 58. Okay, good. B is right. It is non-ohmic. What would the current have to be if it were an ohmic device? Goodness. Like here I have 3 volts and 2 amps. If I go up to 6 volts, what must the current be to be an ohmic device? 4, right? Because I double the voltage, I have to double the current. But here I don't double it, I only multiply it by 3 halves. Goodness. Bless you. All right, so no need to apologize. So B is the right answer here. Oh, how'd y'all do on that? Did y'all do well on that one? Is that joke worthy? It was an easy question, so I'll give you a bad joke. It's not even a joke, it's just sort of a thing that happened to me that was kind of funny. I told you I used to work at a bar, like in Mississippi as a bartender or the waiter too. Great job for us. Well, no, it's a terrible job because the hours are bad, you're out all night, you don't really, you make pretty good money. But anyway, I was there and it's kind of late and this mushroom walked in. I'm serious. A big old mushroom just walks in. And I said, hey, we don't allow people like you in this establishment. And he said, hey, I'm a fun guy. Heard that one before, huh? All right, let's see. Let's look at resistivity. We can think of electricity sort of like water flowing through pipes. So if you have a really big pipe like this, and you got water flowing through it, it's going to go through there pretty easily, right? However, if I have a tiny little pipe like this, and I have water flowing through it, it's going to be harder to push that water through the smaller pipe than it is for the bigger pipe. We can think of resistors in a similar way, that if I have a resistor that's really big, not a big resistance, but like physically big resistor, then it's going to be easy to push electricity through that. It's kind of like a big pipe. But if I have a really thin resistor that's just tiny, like, just a small diameter, then it's going to be harder to push electricity through that pipe. In a similar way, What if I have a pipe that's long and then a pipe that's short? Which one is going to be easier to push electricity through? Is it going to be easier to push electricity through the long pipe, or water through the long pipe, or electricity through the short pipe? Short one, right. So we can get this proportionality for resistance. That is, that resistance is inversely proportional to the area. This is the area over here. That's just saying as A goes up, the resistance to the flow of electricity goes down. It's an inverse proportionality. Whereas for the length, R is proportional to the length. And that says as the length of your resistor increases, then the resistance is also going to increase. It's harder to push water through a hose that's a mile long than a hose that's just a few feet long. And so we have these two relationships, and then we can sort of put them together. There will be a third variable called the resistivity, which is dependent upon the material. And so if we say the resistance is proportional to L, or is equal to L over A, then this rho is sort of like a proportionality constant, or it's a value that's dependent upon the type of material. So different materials have different resistivities. For example, copper wire has a resistivity, and so does wood. Which do you think has the higher resistivity? Copper wire or wood? Wood, because it's an insulator, and so it has a very big resistance. Remember, we had a very similar thing for capacitors. We had this expression for capacitance was epsilon naught A over D. And so I like to think of these very similarly for capacitors and for resistors, that I have these expressions that give me the capacity to store charge or the resistance to resist the flow of electricity that are dependent upon their dimensions. But then I also have these other expressions, V equals IR and Q equals CV, that tells me what happens when I put a certain energy into these to either the current or the charge. So these are very similar in the way we approach them. They're different devices and they operate differently, but mathematically they'll work out very similarly. All right, let's see. All right, I meant to write here too that the resistance is proportional to the resistivity. And then we come up with this. This is on your equation sheet. So we need to memorize it. Well, let's try this. So I think we actually have this a little bit later. But let's try it now. I have two wires. They're made of the same metal. Ding, 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 ding. Think resistivity. So they have the same resistivity. And they have equal length. But the resistance of wire A is 4 times the resistance of wire B. How do their diameters compare? Now remember, R is equal to rho L over A. And I also want you to remember that area is proportional to the diameter squared. The area of a cylinder is proportional to the diameter squared. This is the cross-sectional area. So how do their diameters compare? It's a little tricky. You want to think about which of these wires is going to have the biggest diameter and which will have the smaller diameter. I'll think about that. I need to... All right, if we finish this one, go on to the next one. We'll stop in about 10 seconds or so. I'll stop at 145. 145. Okay, yeah, we're sort of all over the board, and he is right. First of all, you just want to ask yourself the question, which of these has the smaller diameter? Well, the resistance of wire A is bigger than the resistance of wire B. So let's see, if it has a bigger resistance, does that mean that it's a big cross-sectional area or a small cross-sectional area? Small, right. So the wire A will have a smaller diameter than wire B. So that gets rid of options A through C. And then the resistance is going to be 4 times. Now remember, this area is diameter squared. So if I think about my R as rho L over A, then I'm going to say pi times D squared. It's really pi R squared, but it doesn't really matter. We're just looking at the proportionalities anyway. Now, if I have a half of my diameter, that gives me 4 times the resistance. We'll see some other strains of questions like that, but you'll certainly see this on the exam in a couple of weeks, where I ask you, if you change this property about the resistor, what happens to the overall resistance? Similarly, you'll have the same with capacitors. You're looking at the equation and thinking about how these things affect the resistance. Let's try this one. The resistivity is a nice way to determine unknown materials. So, for example, here we have an unknown material. We measure its length and its cross-sectional area, and we put a current across it with a certain potential. And then I can calculate what is the resistivity, and from a table determine what that material is. First you want to find the resistance, and then find the resistivity, and then you can choose the material from this table. All right, let's do about 10 or 15 more seconds. Stop at 2:30. Just guess if you're not sure. 2:30. All right, let's see. I think D is right. Let's take a look. So the way we do this is we first find out what is the resistance. That's V over I from Ohm's Law. And with those values, I get 0.07 ohms, which seems really small, right? But it's a wire. A wire has a very small resistance because, you know, it doesn't really resist the flow of electricity. And then we say, well, I want to know what the resistivity is. So that is R A over L. And I just took this R equals rho L over A and solved that for resistivity. R is 0.07. A, I give you 7.85 times 10 to the minus 7 square meters. You know, it's a wire. That's sort of the cross-sectional area of that wire. And then the length is 1 meter. And I get the resistivity, which is 5.5 times 10 to the minus 8. That's in ohm meters. And then I go through and I see, oh, that's tungsten. All right? So what does a lawyer wear to work? A lawsuit. All right. Good job. You probably see a problem like that. It's a nice way if you have a metal and you don't know what it is. Like if you ever just come across, hey, what kind of metal is this? Then you measure its resistance, you measure its cross-sectional area, you measure its length, you look in your table of resistivities, and boom, you got it. It's like, oh, this is copper, or this is whatever. It's useful. All right, let's look at electrical energy and power. You have some questions about this on your quiz, too, or your OpenStax homework assignment. Batteries convert chemical energy to electrical energy. Which is then converted to whatever it is that you're doing with your electricity, your mechanical or thermal energy or whatever. So it's useful then to be able to describe the amount of electrical energy that's provided by a circuit. Now remember, we defined our potential. We said that potential is energy per charge. That's how we define potential. Right? Fields were force per unit charge. Potential is energy per unit charge. So when I talk about having something that's 120 volts coming out of the wall, that describes the number of joules per coulomb I'm giving to those charges. If I have more voltage, I have more energy, I have more current pushing through. So I can describe my potential energy as Q. Yeah, I'll say delta Q times delta V. So if I look at this as a function of time, because I know that power is energy per time, that is our definition of power. Remember from last semester, power, it's in watts. It's measured energy per time or work per time. And so my power then is equal to delta QV divided by delta T. But now you say to yourself, oh, well, something in this looks familiar because we've seen this already. We've defined this. What looks familiar to you? Does this stand up, this Q over T? It is work over time, actually. But this Q over T is our current. Yes. So our Q over T is our current. So the current, we had defined before in this chapter is Q divided by T. So our power then, if this is our current, we can describe our power as just V times I. So electricians use this a lot when they're, working on your homes if they want to figure out how much power is going to be pulled by a particular circuit so that you don't overload that circuit. We'll get to that later in chapter 4. But they use this expression a lot in order to figure out a certain voltage and a certain power, what current will that circuit draw. So this applies to any electrical device, whether you're doing DC, which is a direct current, which is what we're dealing with, or alternating current, which we'll talk about in a couple of chapters. The unit of power is the what? What is it? It's the watt. That wasn't a question, that was a statement. The unit of power is the watt. Oh, I got you. What was I saying? The unit of power is the watt. If you remember, 1 watt is equal to 1 joule per second. We abbreviate with a capital W. And listen, in all the physics books, they give you these different expressions for power, and sometimes it's useful to know them, and they're all on your equation sheet. But I can just substitute V equal IR in various ways into the power equation and get different expressions for power. So I can get P equals VI. I can get P equal I squared R. That's just saying P is equal to IR. IR times I is I squared R. So substituting Ohm's law into this power equation. I can also say that P is equal to V squared over R. That is substituting I is equal to V over R. And I get V times V over R gives me this. all three of these are on your equation sheet. Don't memorize it. If there's really anything that you memorize, you should just memorize this more fundamental. And then if you need to, get a different value, you can substitute Ohm's Law in or use Ohm's Law to calculate whatever it is you don't know, the voltage or the current. Okay. I think I have some sample. Oh yeah, here's some sample MCAT questions. These are pretty simple MCAT questions, but the ones on the MCAT can be quite a bit more difficult than this. But I just sort of pulled these from a textbook. If a current of one, or from an MCAT book, if a current of 1 amp flows through a current circuit for 5 seconds, how much charge is flowed? Well, current I is Q over T. Q, I want to know what Q is. So Q is equal to I times T. That's 1 amp, 5 seconds. So I've gotten 5 coulombs of charge. By the way, do you know how much current you have in your household circuits roughly? Or what's the maximum current you can get in your household circuits? No, not 60. That would be in the entire house maybe, or at least in a portion of the house. But in a single circuit, you'll know, around 15 amps or so. So just to sort of give you some frame of reference. Some of your circuits are 20 amps. Some of them might even be 30 amps. Look on your breaker box in your house, and often they'll have little numbers stamped into the ends of them, and ends of the breakers, and that'll tell you sort of what maximum current you can have. R for two identically shaped conductors. That means L and A are the same for these, are in the ratio of 1 to 2. So what must their resistivities be? What are their resistivities, the ratio of their resistivities? Well, let's do it as a clicker question. So A or B, is it 1 to 2 or is it 2 to 1? Or C or D, is it 1 to 4 or is it 4 to 1? MCAT, standardized tests in general really like these ratio problems, so it's useful to be able to think about them. Resistivity must be in what ratio in this case? All right, let's stop at 55. 55. You're doing pretty well. Okay, A is right. I know this because my resistance is directly proportional to the resistivity. So whatever ratio I have in my resistance, I'm also going to have in my resistivity. By the way, what if I had a ratio that is like this, where it's an inverse proportionality? Whatever ratio I have in my resistance, 1 to 2, will be flipped for my area. It would be a 2 to 1, because it's an inverse relationship. Or what if I had an inverse square relationship? Or let's say a squared relationship, a quadratic relationship. R is proportional to the radius squared. If I have a 1 to 2 relationship over here, what am I going to have on the right-hand side? 1 to 4, right? Or if I haven't, this isn't the actual relationship for resistance, right? We know actually it's 1 over R squared. And so if I have a 1 to 2 here, I'll have a 4 to 1 relationship over here. Now, I don't ask many ratio type questions on my test, but on the MCAT, they really do like those sorts of questions. So if you're preparing for the MCAT, you need to get to the point where you can think in that sort of mindset. If you're preparing for the MCAT, you should be taking it soon. Do you know that? You should be taking it at the end of your sophomore year. Go ask Dr. Roberster, she'll tell you. You should be thinking about it soon. I know that you haven't had biochem yet, but you've had organic, and you've had physics, and you've had all those 4 or 5 year general chemistry. And students often take it more than once, so you should really consider thinking about taking it. If not this semester, next semester over the summer. Did you know that? Yeah, you should really think about it. Go talk to Dr. Robichaud. She'll shoot you straight. But I'll shoot you straight too, folks. It's good idea to get at least one time sort of before you take it for real. All right. Let's look at a transformer. Oh shoot, this isn't a clicker question. A transformer transforms an input voltage and produces an output voltage that is larger or smaller than the input voltage. The voltage is changed, but the energy is not, so the input power is equal to the output power. You know what a transformer is? Big oil can outside your house. It's about yay big, about this tall. It sits up on a pole. All it is two big coils of wire that sit inside mineral oil. It's filled with mineral oil to keep it from rusting and to insulate it. And what that does, your transformer, you have one coil over here, and then you have another coil right here. Listen, we're not going to talk about AC electricity, but this is fairly interesting because it's what powers our house. What this does is it takes high voltage electricity and steps it down to low voltage electricity. Because you know those lines that are running outside your house? They're like 3,000, 4,000 volts. But when it comes into your house, it's what? 120, 110, depending on how you look at it, we'll say 120. And so we get high voltage coming in, or excuse me, high voltage on the lines, but then a low voltage coming in. And so what this is saying is that I put in a small voltage, but I get out a voltage that's 300% larger. But it says that the energy is not changed. So let's think about the power. I get Vn times In is equal to Vout times Iout. That's to say that the power isn't changing, or the energy doesn't change. But this is telling me that Vout is increased by a factor of 3, because it's 300% larger. So what is the ratio then of Iout to In? Let's try it out. We'll do 1 to 3, 3 to 1, 1 to 9, 9 to 1. What is the ratio of Iout and In? What must the ratio of Iout to In be in order for this to be equivalent? And right now it's not equivalent. All right. Y'all are sort of split on the answer, and that's okay. I'll show you how to get it. I'm going to stop at 110. So 5 more seconds. Just guess if you don't know. 110. Okay, A is the right answer. I know that Iout has to be 1/3 of In. Now, in fact, this is what we call a step-up transformer because the output voltage is bigger than the input voltage. But outside your house, you don't use a step-up transformer. You use a what? A step-down transformer because you're taking high voltage down to low voltage. So what happens to the current? You think you got a lot of current in that lines out your house, or just a little bit of current? A lot or a little? You have any idea? I got low voltage in the lines, or excuse me, high voltage in the lines outside my house and low current. And then in my house, I have low voltage but big current. I got a lot of current flowing through that. So anyway, back to this. Our I out to IN, I'm going to write it as a fraction, would be like 1/3 over 1. And so that's equal to 1 over 3 is I out to IN, which is the same as 1:3, 1 to 3. All right? We'll come back to household circuits in Chapter 4. We'll do quite a bit with those. All right, which light bulb in your house draws more current, a 40-watt or a 100-watt bulb? All right, I'm going to stop at 110, 110. Maggie, please. B is the right answer. So the 100-watt bulb draws a bigger current. I always like to think about this. The 100-watt bulb is what? The dimmer or the brighter of the two? It's the brighter. 100 watts is a brighter bulb. And so in order to get a brighter bulb, that means I need more electrons traveling through it, transferring that energy. So the 100-watt bulb will have a bigger current. But you can think about it too in terms of P equals VI. In your household, V is constant. And so the one with the bigger power has the bigger current. In your household circuit, the voltage is always the same. All right, let's try this one. All right, I'm going to stop at 60, 1 minute. I'll go to 105. 105. Hey, awesome. A is right. A couple ways you could do this. You could first find the current. I is equal to V over R. And that's equal to 150 over 50, which is 3 amps. And then you can say P equals VI. 3 times 150 is 450 watts. And then, or the other way is you could say, look, I know my voltage, I know my resistance. You could say it's just V squared over R. And that would be 150 squared over 50, which is also equal to 450. Remember, this was one of those alternate writings of the power equation. Oh, hey, here's a geometry joke. It's dedicated to Miss McHenry. I'm going to tell you about Miss McHenry, my geometry teacher in high school. I told you about that, right? I was really mean to her. But anyway, why is an obtuse triangle upset, like all the time. It's never right. You've heard that one, Cameron? What? Don't finish my jokes. I don't like that. All right, let's try this one. Bless you, Leanna. All right. I'm going to stop at 115, 115. Okay, good. B is right. Listen, we've already said that the power is 450 watts. This is the same setup. It's 450 watts. And now I want to know what energy in 3 seconds. Well, power is energy over time. And so energy is power times time. And so that's going to be 450 times 3, which is 1350. B is the right answer. All right, I think we have a few more clicker questions on the back, so y'all can turn to your appendix in the back. I think we're done here. Yeah, turn to the appendix in the back. We haven't done this one, but I'm going to skip it because we actually have done it. This was the one that we did earlier. So if you want to circle that answer, that's fine. It was B for 3.38. It's identical to the one we did before. All right. This one's I like this one. This is interesting. So I have a wire of resistance R, and it's stretched uniformly. That means that the volume of the wire is constant. So it's like you start with a wire that's like this, and then you stretch it out, and it gets longer and thinner at the same time. I start with a wire like this, and then I stretch it, and it gets longer so that it's twice the original length, but it still has the same volume. What happens to the resistance of this wire? First, you want to ask yourself the question, does the resistance increase or decrease? And then you might be able to remove some options. Oh, it's the bath. Is it the bathroom? That's the first time I've heard it. It's like nobody goes to this bathroom. Because the bathrooms in Pelton are disgusting. They are terrible, aren't they? I should go to Beauregard. Yeah, go to Beauregard. Oh, I was recording that. Don't tell anybody. All right, I'm going to stop at 145. 145. Okay, yeah, so that's good. The resistance does increase, right? But remember that the volume is equal to the area times the length. So if I make the length twice as long, that means my area gets to be half the area. In general, when I want to know the volume of a three-dimensional object, I take its cross-sectional area and I multiply times its length. That's true for like a rectangular prism or a cylinder. I multiply the area times the length. And now I say R is rho L over A. I'm halving the area and doubling the length. That's going to give me a factor of 4 for the resistance. So E is right here. Factor of 4 resistance. It's interesting, isn't it? All right. When you rotate the knob of a light dimmer, what is being changed in the electric circuit? Are you changing the power, the current, the voltage, or some combination of those? All right, let's stop at 40 seconds. 40. Hey, that's good. D is right. I'm changing both the power and the current. But as I said, the voltage, that remains the same. This isn't a joke. It's seriously not a joke. Like, this is just a story about my mom. She died, 4 years ago almost. But she cleaned houses for a living. And when I was a kid, I used to get to go with her. I'm sharing those special moments here. Sharing. And I used to get to go with her, but in my mind, it was like, these are all rich people. And they had all sorts of things in their homes that we didn't have. Like some of them had a swimming pool. Now we get to swim in the summertime. Some of them had stairs, like in their house. You could slide down the stairs. Some of them had cable TV. And some of them, in their dining room, would have little dimmer switches on the lights. And I would go in. In the lives of the wealthy and famous, it's like a whole different world out there. One time they cleaned a bank, like in the evening time. It was just like an extra job. And I would go into the president's office and sit at his desk. I was like 6 years old. And he had one of those little shoe shiners with the red and the black things that spin. And I would go up and I'd take my old nasty tennis shoes and shine my tennis shoes on his little shoe shiner. Man, rich and the famous. Gotta love them. All right. 2 light bulbs operate at 120 volts. One has 25 watts. One has a power rating of 100 watts. Which one has the greater resistance? We had a similar question before, but this is asking a different thing. Which has a greater resistance? Which resists the flow of electricity the most? All right, we'll stop at 45, just a few more seconds. All right, good. That's right. The 25 watt bulb, we have one more question. 2 space heaters in your living room operate at 120 volts. Heater 1 has twice the resistance. Which one gives off more heat? Heater 1, which has the big resistance, heater 2, which has a small resistance, or both give off the same heat because, they're heaters. Dude, we have like 7 minutes left. What are you talking about? All right, just a second. I'll stop. 40. I'll stop at 43. 43. All right, good. B is right. Listen, The one with the bigger resistance resists the flow of electricity more, so you just don't get as many electrons going through it, so it doesn't give off as much heat. We'll talk more about this on Monday. Y'all have a great weekend.